Assessing resonance structures. When you draw resonance structure for a specific molecule, the actual structure of that molecule is basically a hybrid or blend of all different structures. However, not all the resonance structures contribute equally to that hybrid. Some of them are more important and they may contribute more. There are a few rules that we can use to evaluate the significance of resonance structures, and these rules are listed here in order of importance. We are going to review them together and use them to find the most important resonance structure for the specific molecule. The first rule says that the most important resonance structure is the one that all its atoms fulfill the octet rule. So let's look at the example here. Okay, and let's draw the resonance structure for that. So I can recognize the pattern. Lone pair of electrons next to the carbocation. And oxygen with 3 bonds is positively charged. If you compare these two structures, in this structure we have carbocation. We talked about carbocation before, and we know that carbocation does not have full octet. It only has 6 electrons around itself. However, this carbon has its full octet. Don't forget that we have a hydrogen connected to this carbon, both structures. Okay? Therefore, all the atoms in this structure, they have full octet, so it's going to be the most important resonance structure among these two. The second rule says that the structure with fewer formal charges is always favorable and more important. So look at this example here. Okay, let's draw the resonance structure for this compound. I can recognize the pattern. Again, I have lone pair of electrons allylic to the double bond. So I can use 2 arrows. Now nitrogen with 4 bonds is positively charged. Divalent nitrogen with 2 lone pairs of electrons is negatively charged. Alright. I can also recognize another pattern, which is the double bond between 2 atoms with different electronegativity. So I can draw this arrow and draw the next resonance structure. Okay, so don't forget carbon now is positively charged. Now among these three, which one is the most important one? So if you look at the last one, we can recognize carbocation, so no octet. Therefore, this cannot be a good contributor. So this is not the major one, definitely. Now among these two, both of these structures, all of the atoms in them, they have the full octet. So we need to use the second rule to identify the major contributor. In the second structure, you can see we have formal charges. However, in the first one, we have 0 formal charges, meaning that this one is the major contributor. Don't forget to put the resonance structures in brackets. The third rule says that a structure with a negative charge on the more electronegative atom, it is always more significant. So what does that mean? Okay, let's draw its resonance structure. I have a lone pair of electron allylic to double bond, so I can use two arrows. And don't forget, carbon gets negative charge here. If you compare these two structures, the atoms in both of them, they have full octet. Then if you compare rule number 2, we have negative charge here, negative 1 here, so it's the same. Then we need to use the rule number 3. In the first structure, negative charge is on oxygen, which is more electronegative than carbon. However, in the second one, we have the negative charge on carbon. Therefore, the first structure is favorable. The fourth rule says that we should avoid drawing structures where two carbons have opposing charges. So if you look at this example here, okay, let's draw the resonance structure for this molecule. Again, I can recognize the pattern of allylic lone pair. So I can use two arrows. Okay, nitrogen with 4 bonds is positively charged, and don't forget carbon got the lone pair, so it's negative charge on it. And then I can recognize another pattern, which is the double bond between two atoms with different electronegativity. So I can push arrows here. Okay, so in this case, nitrogen gets the lone pair. Carbon was negatively charged in the first one, and now this carbon gets positive charge. So this structure is not a good structure. It is opposing the rule number 4, so we need to avoid that. We cannot draw this resonance structure. Okay, this is not a good resonance structure. Okay, and among these two, all right, so all of them have their own octet. Then we need to use rule number 2. We have formal charges here, but here the charge is 0, so that one is the major contributor. In this practice problem, we are going to draw all the resonance structures for this compound here and indicate the major contributor. So I start by drawing the lone pair of electrons. Oxygen has 2 lone pairs, so I draw them on oxygen. Then I need to recognize the pattern. By looking at this molecule, what I can recognize is this allylic carbocation. And I can move the pi bond to make a new pi bond. Okay, and this carbon becomes positively charged. Then by looking at this, what I can recognize is a lone pair next to the carbocation. All right. So I will going to make double bond here, and I didn't touch the rest of the molecule. And then I need to calculate 4 mole charge on oxygen. Oxygen becomes positively charged. Now there is one more resonance structure for this molecule, and how I recognize that by looking at this pi conjugated system. So I have double bond, sigma bond, double bond, sigma bond, double bond. So I can move the electrons through this pi conjugated system as well. So this pi bond comes here to make a new pi bond. This one comes here to make a new pi bond, and this one comes here to make a lone pair. So that gives me I made a new double bond here. This one is single, this one becomes double bond, and then I'm gonna have positive charge on this carbon. All right, so there are 4 resonance structures for this compound here. Now, which one is the best one? So we had a set of rules. First, fulfill octet rule. Second, minimize 4 mole charges. And third is negative charge on more electronegative atom. Okay, so we need to follow the order. The first one, fulfill the octet rule. So anything that doesn't fulfill the octet, it cannot be the major contributor. So let's check all the structures here. So in this one, I can recognize the carbocation. And I know carbocation does not fulfill the octet. So that cannot be a good structure. Second one, I can also recognize the carbocation here. So that cannot be a good structure. This one, so I can check and all of the atoms are following the octet rule. That's fine. And the last one, I also have the carbocation. So I don't even need to use the second and third rule. By the first rule, I can identify that this is my major contributor. Now you may think that right here in the first structure, this lone pair is allelic to the double bond. So why I didn't draw the resonance structure for that? So let's try it together. I can push the electrons. I use another color to show that. So allelic, the first arrow makes the double bond, and then the second arrow makes the lone pair. So if I draw the resonance structure by this arrow pushing, I would get a double bond here and positive charge right here, and this carbon becomes negatively charged. So you need to calculate the 4 mole charges on oxygen, and oxygen also becomes positively charged. Now look at here. So what's happening? I have 2 carbons with opposing charges. So this is not allowed. we cannot draw such a resonance structure. Okay, so the blue pathway is forbidden. Also, if you look at this blue structure, not only I have two opposing charges on the carbons, I created a lot of formal charges, like two positive charges and one negative. So it is completely unfavorable. Let's talk about localized and delocalized electrons, the difference between them and why that difference is important. So if you look at these two structures, on both of these structures, I have a lone pair of electrons on nitrogen. However, this lone pair on this structure cannot participate in resonance. There is no pattern here, so we call that lone pair localized electrons. So they are not moving, that's why they are localized. However, in this structure, this lone pair is allelic to double bond, so it can participate in resonance, and we call that delocalized electrons. They can move. Now, if I ask you what is the hybridization on the nitrogen here, nitrogen has 4 connections, so it has sp3 hybridization. Therefore, the localized electrons reside in sp3 orbitals. And if I ask you what is the hybridization on this nitrogen, let's draw the resonance structure for that first. So I can move electrons. This nitrogen is positively charged and carbon becomes negatively charged. It has lone pair of electrons. If you look at the top structure, the hybridization on nitrogen, it has 4 connections. It's sp3. However, in the bottom structure, the hybridization is sp2. Now, how is that possible? So here is the point. If you remember, I told you that we have 2 types of electrons that can contribute in resonance. First, electrons in pi bond. Second, electrons in lone pair. But where can we find these electrons? Where are they located? These electrons are located in the p orbitals. Okay, so this is very, very important point. Remember, only electrons in the p orbitals can participate in resonance. Therefore, because these lone pairs are participating in resonance, so they must be in p orbital, meaning that the hybridization on this nitrogen is sp2. Okay, because the sp2 hybridization can gives us 3 sp2 orbital and 1 p orbital. Okay, however, sp3 can only gives us 4 sp3 orbitals, if you remember. And electrons in this p orbital are participating in resonance. So here is the rule. When you have 2 hybridization, sp3 and sp2, and you want to decide which one is it, always the smaller one wins. So sp2 is the hybridization on the nitrogen. In this practice problem, we want to know what is the hybridization of nitrogen in this structure. So the first step is to draw the lone pair of electrons on the molecule if there are any. Nitrogen has 1, so I put it there. Now I can recognize a resonance pattern. I have allylic lone pair. So I can use two arrows to draw the resonance structure. Nitrogen with 4 bonds gets the positive charge. Now the pi bond form a lone pair on carbon, and we didn't touch this double bond. You can draw more resonance structures for this specific compound, but to answer this question, the first resonance structure is enough. Now let's look at the lone pair, the nitrogen in the first structure. So the hybridization on the nitrogen here is sp3 if we just look at this one. However, the lone pair participated in resonance, all right? Meaning that this lone pair reside in p orbital. Therefore, we need to look at the resonance structure to identify the hybridization. And hybridization in the second structure on nitrogen is sp2. Okay. Now, if you consider the structure of pyridine, okay, by looking at this structure, you may recognize a resonance pattern. You can see a lone pair allylic to this double bond. So you may think you can use two arrows to draw the resonance structure. Okay, negatively charged and nitrogen becomes positive. So you may think of drawing this resonance structure, but actually this is not a valid resonance structure. It is completely incorrect. We cannot do that. Now, why is that? This lone pair of electrons is actually reside in sp2 orbital, not in p orbital in pyridine. So this lone pair all right, and we call that lone pair localized lone pair of electrons. Okay, so since they are these electrons, they are not in p orbitals, they cannot contribute in resonance. So that resonance structure is completely incorrect. Now you may ask, how can you know it? How can you recognize such a thing? So we have a general rule. That general rule says when an atom possesses pi bond and lone pair, they both cannot participate in resonance. Okay, so here in pyridine, this lone pair cannot participate in resonance. However, you can draw a resonance structure for pyridine, and to do that, you need to follow the pi conjugated system resonance. So if you remember from benzene, we had pi conjugated system in the ring. You can move the pi electrons in the ring with 3 arrows here as well. So you can draw a resonance structure for pyridine by moving the pi electrons in the ring. So as you see, I didn't touch these lone pairs while drawing resonance structure. They don't participate in resonance. So this is the best resonance structure that you can draw for pyridine. What is the hybridization on the nitrogens in this structure? So the very first thing you need to do is to draw the lone pairs. This nitrogen, it has a lone pair of 3 bonds, so it should have a lone pair of electrons on it. Similar to that nitrogen and similar to this one. Now, if you look at this nitrogen, this lone pair cannot participate in resonance. We cannot see any pattern, so it is localized electron. Okay. Now, when we have localized electrons, we can easily consider those electrons while defining the hybridization of the atom. Meaning that this nitrogen has 1, 2, 3, and 4 connections. So we can count this lone pair. And 4 connections means sp3 hybridization. Okay. Now if you look at this one, this lone pair is allelic to that double bond, so it can participate in resonance. Therefore, the hybridization on this nitrogen, so this is delocalized, and the hybridization on the nitrogen, so we cannot count this lone pair on the hybridization, okay, because they are in the p orbital. Therefore, I just count these 3 bonds, so the hybridization is sp2. Now, the third nitrogen, I have a lone pair of electrons and pi bond on a single atom. And we had a general rule, not both of them can participate in resonance, alright? So this lone pair is localized. And because it is localized, I can basically consider that while identifying the hybridization. So meaning that this nitrogen has 1, 2, and 3 connections. So I count this lone pair. And 3 connections means sp2 hybridization.